Okay, so it's my pleasure to introduce today Guido-Roberts-Borsani, professor at the University College London. Guido did his PhD at UCL, supervised by Amélie Saint-Onge and Richard Ellis. You get it in 2019, right? Before moving to UCLA as a postdoc to work with Thomas Otreu on James Webb data. And then he moved back to Europe in 2023, yes, as a fellow at the Observatoire de Genève. And he became an assistant professor at UCL in January this year. So today he's going to talk about the JWST view into the physics of the first stars, galaxy, and black holes. Guido.
All right. Well, thank you, everybody, first of all, for coming. And I want to thank the organizers, in particular, Nicolas and Christian, for bringing me over here. I feel like Marseille at this point is almost like a second home. And every time I come back, I'm reminded really of what it means to be a pioneer in this field. So it's great to come back and tell you a little bit about the latest results from JWST, looking at the first generations of stars and galaxies and black holes, and how we can use JWST to understand a little bit of the physics that's going on within the first billion years of the universe. And so that's going to be the topic of my talk today. I'm listing here some of the main collaborators who have contributed to these works over the last few months and last couple of years. And so when I talk about high redshift, what do I mean exactly? So some of you will be familiar with this schematic. It's a schematic representing the history of the universe over cosmic time. On the left, you can see the start with the Big Bang, 13.8 billion years ago. Time is going from left to right, and redshift from redshift 0 on the right all the way to infinity on the left. And so after just the Big Bang, you get this beautiful imprint, the cosmic microwave background, the embers of the Big Bang, essentially. And as the universe expands, so everything is very cool, very hot, and so radiation and matter are coupled together. Once the universe expands slightly, it cools, and all of a sudden the universe starts to form neutral hydrogen. Protons and electrons fuse together to get neutral hydrogen, and we enter what's called the cosmic dark ages. There is a complete absence of UV light. There are no stars yet, no galaxies, no black holes. It's just emptiness after nearly 400,000 years. So the cosmic dark ages. Now, after this time period, this is when things really get interesting, because the first stars begin to form under the influence of gravity. They ignite, and they start emitting copious amounts of very harsh UV radiation. And so these stars form the first galaxies and first black holes. And after a few 100 million years, we start entering this very interesting phase, this last phase change of the universe called the epoch of reionization. So the first stars and the first galaxies start to reionize the surrounding hydrogen around them to form protons and electrons. And eventually, over the course of the first billion years, they complete this process. And after redshifts of 6 or so, the first billion years, we then enter the last sort of phase change of the universe, this ionized medium within which we now reside. And so this time period, what I call the final frontier, the first billion years of the universe corresponding to redshifts greater than 6, is a really interesting moment where we can understand when and how the first stars and galaxies formed. We can understand what the seeds of the supermassive black holes that we see today were, how were they planted into the universe. We can understand what the chemical enrichment histories of galaxies are. In other words, how did the chemistry that we see today, where did these heavy elements come from, and how quickly did they form? And we can also understand which are the sources that drove this reionization process, the last phase change of the universe. And so what you might note is that all of these questions relating to galaxy formation, for instance, how did galaxies assemble their stellar masses, are intrinsically related to this reionization process. One informs the other, so how galaxies assembled their stellar masses, when the first supermassive black holes formed, and how quickly did galaxies produce heavy elements and dust. This directly informs the reionization process, and the outstanding questions now with reionization are: when did it occur? How did the first large-scale ionized bubbles form, and which were the sources that powered this entire process? So this talk is going to be primarily about the galaxy formation part of things, not the reionization part. But I just want to convey the message that studying galaxies at very early times effectively has these cosmological implications as well. One informs the other, and you cannot know one without the other. Up until now, however, the flagship telescope with which we have been looking at the early universe, our window into the early universe, has been the Hubble Space Telescope. And so whenever Hubble would point to blank parts of the sky or lensing clusters, like you can see here on the left, it would reveal hundreds or thousands of galaxies at redshifts greater than 6. All of these UV-selected galaxies. This is the Hubble Extreme Deep Field, one of the deepest images that were ever taken with Hubble. And over here, you have lensing clusters where you can look at faint galaxies. And if you do the most simple exercise possible, which is just count the number of galaxies as a function of the UV magnitude, you get this, which is called the UV luminosity function. In essence, on the y-axis, you have the number density per cubic megaparsec as a function of their absolute UV magnitude. So brighter galaxies are on the left, fainter galaxies are on the right. This is at redshift 7, and you can see there's this very well-defined curve suggesting faint galaxies are the predominant population in the universe. The brighter galaxies are the rarer ones, and just by a simple number argument, you might then say that faint galaxies are the ones that drove this reionization process if you assume all of these galaxies output the same amount of UV radiation. But this doesn't tell us too much about the intrinsic physics of the galaxies. Through models, we can try and understand, through the evolution of the UV luminosity function, how dust may have formed in the universe, how quickly stars formed as well. However, this doesn't directly inform what we know about the ISM and the stellar populations of these galaxies. And before JWST, the only way really to study these galaxies in terms of their ISM contents and stellar contents was through ground-based spectroscopy and the use of the combination of HST and Spitzer. And this was exclusive to the very brightest populations. The fainter populations were beyond the capabilities of our foremost telescopes. So in 2019, I arrived at UCLA just before the arrival of JWST, and I was chatting to a postdoc over there, Louis Abramson, and I was saying, Louis, you know, this is going to be incredible. JWST is going to give us all of these galaxies. We're going to study the ISM, the stellar populations, black holes. We're going to find out so much about the early universe that we've never figured out before. And Louis sort of summarized this depressing prediction, really, of our field, encapsulated into this one sentence. He just said, let me guess, they're small, blue, and bursty. And so I said, OK, well, I'll hold you to that prediction. Let's talk again in 3 to 5 years and see how that prediction holds. And Louis, of course, was not completely wrong in a sense. He was basing this on fact. Here, if you plot what was state-of-the-art results for Hubble and Spitzer, you can see the galaxies, their sizes here. I'm plotting their size as a function of redshift. For redshifts 8 to 10 galaxies, there are not that many. There were maybe 20 to 30 sources selected with Hubble. You can see they're on the order of a kiloparsec in size. There's not too much variety. There's not that much interesting here, but they are on average small. You can look at their UV continuum slope. So in essence, their colors based on the stars within them. They are on average blue galaxies, even as a function of redshift here. Not too much evolution, a lot of scatter. And then if you model their fluxes with galaxy evolution models, you might look at their star formation histories. That's what I'm plotting over here. An SED, a spectral energy distribution as a function of wavelength. In essence, their mock spectroscopic profile, let's say. And on average, you would think that they are young. So, Louis' prediction was based really on this sort of limited view based on Hubble and Spitzer. But to really understand the physics of what's going underneath the hood in these galaxies, we were really dependent on Spitzer. And so this is the HST and Spitzer photometry of a faint redshift 7.5 galaxy. This is a nice plot by Ryan Ensley. And the Spitzer points are here at 3.6 and 4.5 micron. And you see, you could fit these data points with a template of what would be actually quite a mature galaxy, a galaxy which on average is about 500 million years old, which has a stellar mass of 10 to the 9 or so. However, these data points are not that constraining. What you see is you could equally fit this galaxy with a template that's 2 orders of magnitude lower in stellar mass and has an age of 3 million years. And so you have factors of about 100 in uncertainty in stellar mass and age on these galaxies that we then aim to probe with JWST. So we're really sort of constrained by the depths of the Spitzer imaging to constrain the physics of what's going on in these galaxies. So this is all with photometry. We, of course, have ground-based spectroscopy as well, for instance, from Keck and the VLT, ALMA as well, which obviously were there before JWST. But really, with Keck and the VLT, the only sort of lines we could probe were the so-called Lyman alpha line. So Lyman alpha, as you can see in the plot on the left, this is a galaxy spectrum in the UV at redshift 3. Lyman alpha is this very bright line. It's the brightest line in the UV spectrum of galaxies, which is created by the presence of very young stars and stellar populations. However, all the flux at wavelengths blueward of this in a neutral medium gets scattered by intervening hydrogen along the line of sight. So as you go to higher and higher redshifts, redshift 6 and above, where we've seen before the intergalactic medium changes from ionized to neutral, you start then getting an absorption of all of the flux blueward of this Lyman alpha line. And so the sort of first order approximation is that in a neutral medium, which is what you're seeing here in this middle plot, these lines here represent neutral hydrogen. If you see Lyman alpha, it's because you have an ionized bubble around these galaxies. They have been able to ionize their immediate surroundings, and Lyman alpha then is redshifted out of resonance, and it goes along. So Lyman alpha is not expected in a neutral medium. However, some interesting galaxies revealed Lyman alpha profiles. This was state-of-the-art, basically, data prior to JWST, and suggesting that there were the presence of some very large-scale ionized bubbles in early times. So this was one of the sort of spectroscopic probes we could use prior to the arrival of JWST. And again, I just want to remind that this was really state-of-the-art at redshift 7 or so. We might then logically ask ourselves whether the presence of Lyman alpha in a neutral medium suggests extreme intrinsic properties. Maybe you have supermassive black holes or very massive stars which blow out, ionize this hydrogen around them. And one way we can do this is to look for very high ionization lines. So this is a nice plot by Anna Felter et al. Shows you here arbitrary levels of flux as a function of photon energy and the transition energies for different elements. So over here, for instance, you can see the photon energy required to excite carbon-3, carbon-4 over here, for instance, and nitrogen-5 over here at about 78 electron volts. And what this is showing you is that these low metallicity tracks, these low metallicity star formation, cannot probe the photon energies required to excite these sort of lines. And so one avenue which was used prior to JWST was to try and look for these very high excitation lines, which we then suggest is a signature of AGN, since AGN and energetics are the only energetics that are able to ionize these lines. So here are two examples. You can see carbon-3, which traces metal-poor star formation over here, and then a very, very faint signature in a redshift 9 galaxy of nitrogen-5 over here. So again, this is what we had to work with prior to JWST. And then finally, we want to ask ourselves also, are these galaxies perhaps enriched in metals and dust, and does this suggest something about their stellar populations? This is, again, the spectral energy distribution as a function of wavelength of two galaxy models. Here you have HST and Spitzer photometry. And ALMA here provides some very useful constraints. ALMA probes in the far infrared, and this can constrain basically the two different models over here, two which are relatively high mass. But the big difference then comes in the amount of dust that is required to explain these two curves. And so ALMA, really, the constraints from this together with HST and Spitzer tells you something about the stellar populations that are within the galaxy, the metal enrichment by supernovae, and then the amount of dust grains that are already available in these galaxies. And again, to showcase the state-of-the-art data that we had prior to JWST, this is an oxygen 3 line detected with ALMA at redshift 9, and then here you have dust continuum detected at redshift 8 or so. So HST and Spitzer and ground-based spectroscopy really set the scene for what was to come with JWST, but knowledge of the intrinsic physics of galaxies within the first billion years was really limited by the depths and sensitivity of Spitzer imaging and the sensitivity of ground-based spectroscopy. And so in this sense, JWST really has blown things out of the water. This is one of my favorite images of the Abell 2744 cluster taken with the NIRCam instrument on JWST. And really what's crucial here is JWST now extends both our imaging and spectroscopy out to 30 microns, from about 0.6 to 30 microns. Prior to that, we were, with imaging, we could go out to 4.5 microns, and with ground-based spectroscopy out to 1.2 microns or so. And so now we have this unprecedented sensitivity and wavelength coverage with which to unveil the physics of the earliest sources after the Big Bang. So to sort of summarize, I think, the state of the field prior to JWST, this is the star formation rate density of the universe, in other words, the integral of the UV luminosity function. How many galaxies are there per unit volume as a function of redshift? And you can see with Hubble, you mapped out this sort of decline, right, out to redshifts of 10 or so. After redshifts of 10, there was a dearth of galaxies. Hubble wasn't finding anything beyond that redshift, and so the implication was that cosmic dawn, or the arrival of galaxies, was somewhere around there. I try and summarize this with this quote here, which I think is pertinent. In theory, there is no difference between theory and practice, but in practice, there is. And that's because if you ask a theorist, they would say, well, everything looks fine. Everything goes very well with the observations over here. This is a curve of constant star formation efficiency, which is linked to the dark matter profiles. So it's telling you that galaxies and their dark matter profiles form together. However, then in the first months of JWST data, galaxies were immediately found beyond a redshift of 10, so very bright galaxies. Here are two examples over here. You can see this convincing break, which tells you you're in a neutral era of the universe. These are galaxies at about 25, 26 AB. So in terms of brightness, minus 21, minus 22, these are some of the brightest galaxies known. This was a paper led by Marco Castellano, and I always like to tell this story with Marco in the GLASS collaboration. These were the first observations taken with JWST, and Marco was very depressed at the idea of writing this paper prior to seeing the imaging, because the predictions were that we would find 0.1 of these galaxies in the little field that we were observing. So he said, there's no point in writing this paper. We're not going to find anything. And then within the first week, 2 galaxies came about. Of course, other teams since confirmed these elevated number densities, and it's very difficult then to understand how there are so many bright galaxies at such high redshifts, extending now all the way to redshift 16 or so. Now, a number of solutions have been suggested to explain the brightness and number density of these galaxies, either that the star formation efficiency, in other words, how efficiently you form all of these stars, is changing. It might be a non-universal initial mass function, so you're changing the parameters, of our assumptions. Stochastic star formation histories are one option as well. So these galaxies are very bursty, and maybe they go through a phase where they temporarily become brighter before dimming down again. Or perhaps they've formed dust, and dust obscures young star formation, and they've ejected this dust, revealing this sort of UV bright core. So a number of solutions have been postulated, but these all require testing. And prior to testing them, of course, we need to make sure that all of these galaxies, which remain galaxy candidates, are first verified with spectroscopy. In other words, are they at the redshifts that we think they are? Some of these are not, for instance. This was one of the most confident redshift 16 galaxy candidates, far beyond the redshift horizon set by Hubble at redshift 10. We're now probing only a couple of 100 million years after the Big Bang, or when the universe was about 2 to 3% of its present age. So you can see the photometry here from NIRCam traces this sort of break, which tells you you're in a neutral era. But then the spectroscopy, which is this bottom plot here, tells a different story. You can see the spectrum here in these sort of red lines. The SED that you see here at the top is shown here again. And actually, this is a redshift 4.9 galaxy with these very strong emission lines. And what's happening here is these emission lines are boosting the fluxes to mimic this break over here, which says at high redshift. If you subtract the contribution, you can see from these red squares how this no longer looks like this convincing break. It's just this sort of steady decrease. So this highlights really how spectroscopy is fundamental in understanding the galaxies that we're probing with our imaging with JWST. But of course, NIRSpec has been remarkable in its ability to confirm distant galaxies. And these are two examples. On the bottom, you're seeing one by the GLASS survey, this beautiful galaxy where you see this very convincing break. So everything blueward of this break is absorbed by the intervening hydrogen along the line of sight. And it has these crazy rest frame UV lines, you know, these UV lines from carbon and nitrogen and oxygen as well, all these crazy lines. This is the current redshift record holder, a redshift of 14.4, corresponding to about 300 million years after the Big Bang, led by Rohan Naidu. And putting all of this together, really, this tells a little bit of a complex story. So I've listed here what I think are the sort of three major discoveries over the last couple of years relating to the highest redshift galaxies. The first is over here. I'm plotting absolute UV magnitude, so their brightness as a function of age of the universe. And some of these bright galaxies, now confirmed with spectroscopy, are very hard to explain in terms of their brightness. In other words, how did they get so bright? You really have to have very, very young stellar populations. The efficiency of star formation has to be ramped up to levels which start to become uncomfortable. And so it's really difficult to explain these. If you look at the UV spectra of some of these galaxies, like you're seeing over here, you might notice that there are lines from carbon, but there are also lines from nitrogen. Nitrogen-3, nitrogen-4, for instance. And if you use these to derive chemical abundances and trying to understand the chemistry within these galaxies, you find that nitrogen levels are enhanced relative to everything else. So we do this relative to oxygen because we understand oxygen production very well. And if you plot the abundance of nitrogen over oxygen as a function of galaxy overall metallicity here, you can see low redshift samples here in black, and all of these high redshift samples here are significantly higher than the local samples. And this is interesting because simulations are not able to explain this enhancement in nitrogen. We understand how oxygen is produced, we can explain how carbon is produced, but it's very difficult to explain how we produce so much nitrogen relative to everything else. So a couple of hypotheses have been suggested, either the presence of very rare supermassive stars, which have really yet to be sort of observed at these redshifts, potentially a variable initial mass function. So again, we're having to completely change the framework of our physical interpretations, or just exotic yields from exotic stellar populations, for instance. And then the third one is this Lyman alpha profile. Again, I remind you, Lyman alpha gets attenuated in a neutral medium. So this is a redshift 13 galaxy when the universe was about 300 to 400 million years after the Big Bang. The intergalactic medium is supposed to be greater than 80, 90% neutral. We're not supposed to have formed large-scale ionized bubbles yet. And yet this prominent Lyman alpha line suggests there's already a large-scale ionized bubble around this galaxy. And so this suggests, how did that galaxy form this large-scale ionized bubble? Does it reside in an overdensity with lots of other galaxies around it? Does it have some particular intrinsic physics? What's going on there? And so really the question here is, are these galaxies representative of the general population of galaxies at high redshift? Or do they trace a very special class of galaxies which are missing in our physical understanding and our simulations? So to answer this question, what we need is a spectroscopic benchmark with which to compare to. So we need a sort of model, let's say, with spectroscopy, and we can now do this because at high redshift, we now have the spectroscopic numbers to understand what are the average properties of these galaxies at very early times. So this was a paper we put out now a year and a bit ago. This is absolute magnitude as a function of spectroscopic redshift. Prior to JWST, this plot was filled out roughly here with about 60 objects. Just to give you an idea, we now have over 2,000 objects at redshift greater than 5. Now, for those working at redshift 0, that sounds pitiful, 2,000 objects. But you know, as a reminder of where we've come in only 2 to 3 years, this really is a remarkable increase. And we can now take all of these spectra and derive average spectra, like this one. So this is just a stack a median spectrum of everything that you saw in the previous plot. And all of a sudden now, we're able to get diagnostics which we could only dream of with Spitzer and HST. Just to give you a few examples, over here we have the UV continuum, and the slope of this continuum tells us something about the dust content and the stellar ages of young stars. We then also have these emission lines from carbon-4, helium, oxygen, carbon-3. This tells us about the star formation activity in very metal-poor conditions. We then have the rest frame optical continuum here, which gives us information on the nature of more mature stars, stars which live on the order of 50 to 100 plus megayears rather than just a few megayears. And then finally, we have these very strong emission lines here from oxygen, neon, hydrogen, etc., which gives us information about the dust and the metal contents of these galaxies. So all of a sudden, we're able to go from just estimating some stellar masses from photometry to all of a sudden getting all of these parameters for these kinds of galaxies. And we can split this up into redshift bins to see how these galaxies are evolving based on their spectroscopic measurements. That's what you're seeing here. You're seeing average spectra as a function of redshift, more or less, going from redshifts 5.5 or so out to redshifts 11 almost. So this corresponds to more, roughly about 1 billion years of evolutionary time. And we can plot, the resulting measurements. This, for instance, is what is called the Balmer break at around 4,000 angstroms. Now, the Balmer break, which I'm showing you here at the bottom, this is the spectrum again, is simply the ratio between the rest frame optical continuum emission to the rest frame UV emission. And this tells you, this translates to an age for the stellar population. So the larger the ratio, the more mature the age of these galaxies. And so that's what I'm plotting here as the red points. And interestingly, what you can see is there's this clear increase. That tells you that galaxies are not all forming instantaneously. They form, they evolve, and they become more and more mature. And so as you're looking to earlier and earlier times or higher redshifts, you can see galaxies are getting progressively younger. We can then plot their UV continuum slope, which I showed you is an indicator of the dust content in these galaxies. So that's, again, what you can see over here with the spectrum, the slope of the UV continuum here. And this tells you how much dust is building up. It's quite flat out to redshift of 7. And then all of a sudden, you see this uptick. And so galaxies are producing dust very, very rapidly at later times. So they are quite pristine. And then finally, we can map out the metal buildup. So it is more of a statistical probe, let's say, to the earliest generation of galaxies. We know that the buildup of metals takes time. And so if you can measure their metal content and rewind the clock, you can, in theory, get back to a time when these galaxies are pristine. So this is overall metallicity here on the y-axis as a function of redshift, using these very strong diagnostic lines rather than templates fitted to imaging. You can see this steady decrease, the blue points, which shows you this steady decrease towards early time. So galaxies are becoming more and more pristine. Now, for those of you who may or may not work in metallicity studies, this is based on what we call strong lines. So there's these very strong lines here, which are an indirect probe of metallicity. They are calibrated to true metal contents, let's say. And so we want to improve on this, and this is a program which recently got approved. We'll have nearly 70 hours of NIRSpec time on JWST to try and get gold standard metallicities. In other words, metallicities which make use of the electron temperature in the interstellar medium. Up until now, so this requires this very faint oxygen line over here, which is sensitive to the electron temperature in the interstellar medium. Up until now, at redshifts greater than 6, we only have something like 10 to 20 objects with this line. We will improve on this by a factor of 5 by getting 100 galaxies at redshift greater than 6 with this measurement. So it's a little advertisement. What about probing to even higher redshifts? So we've gone out to redshifts of 10 or so, but even higher redshifts are interesting, going to within the first 500 million years after the Big Bang. And why is this interesting? It's because you're starting to approach the initial conditions that were set for star formation and galaxy evolution, and also the first supermassive black holes. So we can start testing the initial conditions of the earliest generations of galaxies. And these are all galaxies that remarkably have been confirmed at redshift greater than 10. This is just a sample, and it's to illustrate how remarkably easily James Webb has been confirming these sources. And if you pay attention to the rest frame UV part, you can see again this drop in flux every single time, which indicates absorption by intervening hydrogen, blue word of Lyman alpha, in a neutral medium. But you can also recognize some of these booming rest frame UV lines, which we were not expecting before James Webb. And so this is, two examples to highlight this really remarkable diversity in the spectral profiles of these galaxies within the first 500 million years. And so a logical question is to ask, with such little evolutionary time, less than 350 million years of evolutionary time, how do these early galaxies look so different? What are the physical processes that showcase two different spectra like this? And in essence, does this diversity trace different evolutionary pathways, or do they trace the same pathway, but at the extremes? And so this is a question that we aimed to answer over the summer. One way you can probe this is by, first of all, characterizing the distributions of galaxy properties and understanding what drives those distributions. And then you can look at whether those remarkably sort of odd extreme galaxies, whether they fall within the parent distribution of galaxies, or whether they form a distinct population, which would suggest a distinct evolutionary pathway. So this is what we tried to do now that we have a significant number of conformations at redshift greater than 10. This is just to highlight again, I've shown a number of versions of these plots. Brightness, UV brightness effectively, so brighter galaxies at the top, fainter galaxies at the bottom as a function of redshift. We're now going not from redshifts 5, but we're going from redshift 7.5. In gray, you can see photometric points, so these are candidate galaxies. We don't have spectroscopic redshifts for them. The blue squares are all spectroscopic conformations. And I just want to highlight this source, GNZ11, which I'm sure a lot of you will have heard of about already. This was the only spectroscopic conformation we had at redshift greater than 10 prior to JWST. Now, within only a couple of years of JWST NIRSpec time, we now have 40 sources confirmed at redshift greater than 10. Now, for those working at redshift 0, this sounds pitiful. I almost feel embarrassed to talk about statistics with 40 numbers, with 40 sources. But this is remarkable for someone working in high redshift studies, because now we can start to do some population level studies. So in this particular paper, we confirmed 8 new sources at redshift greater than 10. This is the largest spectroscopic sample at redshift greater than 10 with 40. This includes lensed objects, which we otherwise would miss because they're too intrinsically faint. But predominantly, this is characteristic of the bright end of the UV luminosity function. And we can start doing this exercise that I mentioned before of mapping out the distribution of their properties and understand where these apparently extreme sources might fall, whether they are clearly distinct or whether they are part of the overall distribution. So this is what we aim to do. So I showed you some examples before of these nitrogen emitters, or these sources with crazy rest frame UV lines. These are what we consider the abnormal population, the extreme population that we cannot explain. And so these are showcased in blue here, blue squares. This is the equivalent width or the strength of their strong carbon-4 line as a function of UV magnitude. The gray are objects where we don't detect that line. And if we stack these two populations, these are the spectra that results. You can see in the dark blue these remarkably strong UV features from carbon-3, nitrogen-3, oxygen-3, et cetera, compared to a much more, let's say, boring spectrum in a way here in the light blue. And so this really sort of highlights the remarkable diversity of the spectroscopic signatures that we get at redshift greater than 10. So why don't we start then by characterizing the distributions of the observables we get from these spectra, in particular starting with carbon-3. Now, carbon-3 is a measure of the amount of star formation activity that you're getting in low metallicity conditions. So with higher equivalent widths, this is the equivalent width as a function of spectroscopic redshifts. In light blue, you're seeing objects without this strong carbon-4, so these normal objects in a way. In dark blue, you're seeing the so-called extreme objects with this very strong carbon-4 line, which takes a lot of energy to excite. And you can see there's this increase from redshift 5 all the way out to redshift 13 or so. This continues to increase. The numbers are very small, but at redshift 13 or 14 or so, you can see that there's a potentially a turnover. This turnover is expected at some point, so galaxies are becoming more and more bursty, if this is a tracer of star formation activity. But at some point, it's not just burstiness which regulates the strength of this carbon line, it's also the amount of carbon. So at some point, you get to galaxies which are so pristine, so metal poor, that you just don't have enough carbon. And so you expect this turnover as you go to more pristine conditions. So these are half of the objects which only tell half of the story, because the other half showcase just upper limits and suggest actually then that there's a lot of objects where you don't expect so much star formation activity, which is, you know, sort of somewhat remarkable given we're talking about the very youngest times where you have just the youngest stellar populations. And what we can do is characterize the intrinsic scatter here of the overall distribution, and we say relative to this intrinsic scatter, are these exceptional objects distinct, or do they form part of that intrinsic scatter? And you might notice they are right on the edge here. They are the most extreme carbon-3 emitters, pardon me, but they are part of that intrinsic scatter, so they are part of that overall distribution. So this is carbon-3. We can try to then explain whether these differences in carbon-3 that we see from these objects, whether they are due to a difference in metallicity or whether they are primarily due to a difference in star formation activity. And so we can stack these spectra in the parameter space to get average spectra and high signal to noise. And this is what you're seeing, the same plot here as before, except this time as a function of overall metallicity. And these are for stacks of galaxy spectra as a function of equivalent width. So you can see this difference in equivalent width that tells us that the upper limits we saw before are not driven by the depths of our observations, but they are in fact physical upper limits. And we estimate the metallicity of these galaxies, and we see there's a very modest amount of difference in metallicity. So it's not metallicity differences which are driving the differences in equivalent width. However, it tells a different story if you scale the size of these symbols as a function of the very recent star formation activity. In other words, let's say a burstiness parameter. So that's highlighted here. The smaller stars represent a weak burst. The larger stars represent a much more stronger burst of star formation at recent times. And you can see this correlates very, very strongly with the amount of the strength of carbon-3 over here. And the gold star are these sort of extreme objects with carbon-4. And you can see they are the burstiest objects. And so effectively, this difference is shown through star formation activity. We can then look at the UV continuum slope of these galaxies, right? You see a large range of objects, so the color of these galaxies tells you something about the stellar populations and the dust contents within these sources. We find that these sources actually harbor no dust at all from their spectra. So they are dust-free at this point, which means dust cannot be what is regulating the colors of these galaxies. It is actually the ages of the stellar populations which regulate these galaxies. And again, these carbon-4 emitters, generally speaking, reside at the bluest end. So you have red galaxies up here, blue galaxies here. They're the ones that reside at the bluest end, suggesting they are dominated by the youngest stars, stars that live on the order of just a few to a few tens of million years, rather than on the order of a few hundred megayears. However, there's significant scatter, and if you go to these sort of redder slopes here, these are dominated by galaxies with stellar populations already of 50 to 100 megayears or so. This is telling you that galaxies are not all blue, they are also a little bit red, and so there's this evolution of stellar activity. Crucially, however, you also see these 5 objects here, which lie well outside of this intrinsic scatter and cannot be explained just from the age of the underlying stellar population alone. They do not have dust, at least that we can tell from their spectra, so it is possible that these might host supermassive black holes which drive up the redness of these galaxies. So I won't go over that. But then another parameter we can look at, for instance, is also the sizes of these galaxies. We might think that all of these sources are very, very small, given their small evolutionary time and early ages. But you can see these sources vary from about 100 megaparsecs all the way out to about 1,000, parsecs, not megaparsecs, about 100 parsecs all the way out to about 1,000 parsecs. You can see this sort of duality in the distribution of their sizes. And carbon-4 emitters in the blue reside almost exclusively at the smallest end. They are effectively unresolved in the images, so they are very, very, very small. And so if you overplot models that we derive from photometric studies, for instance, this is consistent with what one might expect from the presence of stellar disks already at these high redshifts, and also mergers. And so this suggests that this sort of bimodal distribution might be tracing both stellar disks and merging activity in these sources. Stellar disks implies that there's some sort of equilibrium that has already been in place. And this is seen in simulations. This is not completely unexpected. Over here on the y-axis, you have the size of the galaxy as a function of stellar mass, which in this case is also a little bit of a function of time. This is a simulation. And you can see for this one object where it oscillates between larger sizes down to compact sizes, down to up to larger sizes as a function of time, as it's accumulating stellar mass. And what's happening here is this burstiness. Effectively, when a galaxy is having this burst of star formation, that localized star formation outshines the rest of the disk. It appears much smaller, and then as the burstiness finishes and the galaxy enters this phase of lulling star formation, let's say, you can see the rest of the disk, and it seems to sort of expand in a way. And this is sort of what you're seeing. This is, again, a simulation. Do we see any evidence for this, in individual sources? And the answer is yes. This is a really nice example by Seiji Fujimoto, where you have here this galaxy confirmed at redshift 6 called the Cosmic Grapes Galaxy. On the left, you're seeing the HST image, and on the middle, you're seeing the NIRCam image on JWST, and this is a lens source. What you might see is you have all of these pockets of very intense star formation, and when you deproject this into the source plane, you end up having a disk, a rotating disk already in place of about 700 parsecs, which is nicely consistent with the objects you see here, and 15 star-forming clumps of about 20 to 60 parsecs, similar to here again, which encapsulate about 70% of the total light of this galaxy. So that really highlights this sort of burstiness nature of these early galaxies. Now we can test this a little bit more explicitly by fitting each of these sources with an SED and figuring out what their star formation histories look like. So this is what I'm showing you in these two leftmost panels. So these are the star formation histories of average stacks of these galaxies at redshift greater than 10. So star formation rates as a function of look-back time. So recent times on the left, you're looking back in time as you go to the right. The top panel shows you all of these objects where you might think there's a lot of star formation going on, objects with blue UV slopes that have high carbon-3 equivalent width, etc. And on the bottom, you're seeing the same, but for objects where you think there might be more passive star formation activity, red UV slopes, etc. And what you might note is that when you go to about 5 to 10 million years, all of these star formation histories are sort of, multimodal. They showcase this burstiness of star formation at early times, so they look more or less all the same. However, then once you get to the first 1 to 3 million years, this is where things get interesting. And this is where you can see that actually the sources with the observables which trace star formation, so the ones with the burstiest star formation, have the burstiest star formation histories. So let's take a few examples over here. These are these exceptional objects with very strong carbon-4, these extreme objects, and they're highlighted in gold here. Over the first 1 to 3 million years, the most recent times, you can see that they are the burstiest galaxies over here. That suggests that these sources are dominated by the most extreme underlying conditions with the youngest stellar populations and the most extreme radiation fields. And then if you look at those with strong carbon-3 equivalent width, but no carbon-4, you can see that it's slightly reduced, this burstiness. And that's what this spectrum shows you here. No carbon-4, but strong carbon-3. And then if you go to the lowest one, this blue line over here, which is weak in carbon-3, this is the resulting spectrum. And I think this is remarkable because you see a complete absence of any emission lines. Now, these emission lines, of course, come from star formation activity, which suggests you have this lull in star formation activity. So you're seeing here not a passive galaxy, of course. These galaxies are very young, and we expect they will ignite star formation again and burst. But you're seeing this sort of cycling of bursty star formation directly from the spectroscopy and modeling of this spectroscopy. So is this burstiness or this bursty star formation expected at high redshift? The answer is yes. So this is a nice paper put out by your very own Laure Ciersla. This is showing the fraction of galaxies as a function of redshift based on whether they are dominated by bursty or stochastic star formation or secular star formation, where these galaxies have sort of entered into equilibrium effectively. And you can see that as you go to earlier and earlier times or higher and higher redshift, the number of secular star formation dominated galaxies decreases, and the number of stochastic star formation dominated galaxies increases, particularly at redshift sort of 8 to 10 or so. And this is highlighted again nicely, the imprint on the observables that we see with the spectra. These are 3 different panels, just based on very simple models, let's say, simple stellar population models. You can see the absolute UV magnitude on the y-axis as a function of age. The first 1 to 3 million years, there's not too much activity on the overall UV brightness of the galaxy, but then after that, it decreases very rapidly. So you can see how the effect is perhaps pronounced on the emission lines, but not the overall brightness of the source. This is the so-called Balmer break of those galaxies. In other words, the amplitude of the optical flux to the UV flux as a function of age. 1 to 3, you see quite a big difference over here as this increases. And then here, this is the equivalent width of strong lines as a function of age. And you can see it's again within the first 1 to 3 million years where you see this very different range of equivalent widths before it sort of settles in. So you can see this burstiness of star formation is what's dominating these early spectra. Now, I talked very briefly about whether these, how some of these high redshift galaxies show these enhanced nitrogen over oxygen abundances, suggesting that perhaps there's the presence of massive stars or a different IMF, etc., compared to low redshift. And the hypothesis here is, well, if these galaxies are dominated by star formation and they have enhanced nitrogen, maybe this enhanced nitrogen is due to stochastic star formation and, just extreme star formation rather than exotic physics that we need to invoke. So here, you can't see it super easily, but there are the presence of these nitrogen lines in these carbon-4 strong emitters rather than in the more normal population of galaxies. And if we do a similar plot here, this is nitrogen over carbon. It's a function of carbon over oxygen. Local galaxies are here in blue, and these high redshift galaxies in black. This gold star is the stack of carbon-4 emitters. You can see that they are supersolar in nitrogen over carbon, and they are consistent with these nitrogen-enhanced galaxies, which are significantly different to the local galaxies here. We can compare these to globular cluster stars in the aurora component of the Milky Way, and you can see that they are somewhat consistent. And so whilst this association is not direct, this suggests that whatever might be driving this strong carbon-4, this intense and bursty star formation, may also be driving this nitrogen enhancement, suggesting that this nitrogen enhancement is a generic form of star formation rather than requiring tweaking to our physical frameworks, for instance. So what I think we're seeing is this, effectively, where you get, this is a nice adaptation from Will McClymont at Cambridge, who did these simulations with nitrogen over oxygen as a function of time. What happens is you have these supernovae, these core collapse supernovae, which produce this oxygen around young stars. The feedback from these stars pushes these oxygen clouds out, and you're left with longer-lived AGB stars, which enrich the galaxy with nitrogen. That gas then mixes together when you get a fresh infall of gas, and subsequent bursts, then you see this enhanced nitrogen over oxygen system compared to more pristine bursts. And you can see here 3 different examples of galaxies in Will's simulations. The black tracks showcase the carbon over oxygen, iron over oxygen. The green showcases nitrogen over oxygen, and the purple shows you carbon over oxygen. And what you see is that there are these strong peaks in nitrogen over oxygen which occur after a burst of star formation. So Will's interpretation of this scenario is exactly in line with what we see from the spectra of redshift greater than 10 objects. Now, I know a lot of people also work on supermassive black holes, Now, JWST has opened this parameter space. This is the bolometric luminosity of black holes as a function of redshift. Prior to JWST, this cloud of gold was what we were able to probe with ground-based facilities, etc. And JWST has now opened this parameter space into fainter supermassive black holes. However, it's challenging to explain some of these at particularly early times. This is what you're seeing here on the y-axis, black hole mass as a function of redshift. And effectively, what you want to do is look at your redshift 6 quasars. You derive a black hole mass for some of these early objects, and you say, well, what seeds do I need, and which evolutionary tracks do I need to produce these black holes and these quasars ultimately? And this is quite difficult to do because you need really, really high efficiency to produce these overly massive black holes. So we can ask ourselves, well, within our sample of redshift greater than 10 galaxies, do we already see the signatures of supermassive black holes? Now, it's very difficult to do this. We have to compare our observational signatures to photoionization models. So here you're seeing, again, the equivalent width of carbon-3 as a function of carbon-4 over carbon-3. And the idea here is that you need very high energies to produce carbon-4. And so the higher you are in carbon-3 and the higher you are on carbon-4 over carbon-3, you start touching into this regime of AGN rather than star formation. But you can see half of our points, at least, are consistent with this star formation models because of their low equivalent widths in carbon-3. However, a lot of these objects are, to some degree, consistent with both of these models, including the stack of carbon-4 exceptional emitters. So we cannot say for sure whether these galaxies have some contribution from supermassive black holes or not, but there is no standout evidence that these galaxies have already formed supermassive black holes. There is evidence for extreme star formation, but we do not see evidence in their spectra of supermassive black hole activity. And what's lacking at the moment is this longer wavelength data where you can probe rest frame optical lines with MIRI to try and disentangle AGN activity from star formation activity. So I'll finish up here by saying this is, I think, the scenario that we're seeing where galaxies at redshift 5 to 10 are already in this sort of equilibrium mode of evolution. They are already building up metal and dust contents, and they form stars in this sort of secular fashion. But once you get to redshift greater than 10, things start changing. Galaxies start becoming dominated by stochastic star formation, and this sort of flickering, I think, of these galaxies suggests that we are starting to probe the very first instances of galaxy formation. And so this is sort of nicely encapsulated by this schematic by Michael Topping, where here on the right, so on the bottom plots, you have the star formation rate history, effectively, and a burst of star formation. In the middle plot, you have your stars and the interstellar medium. And then on the top, you have the simulated spectrum. And so you can see if you have just a very small burst, you have a few low-mass stars, effectively, or high-mass stars, but that are short-lived. You have very faint signatures in carbon-3 and oxygen-3. There's a complete absence of these remarkably strong rest frame UV lines that characterize these extreme objects. But once you start increasing the size of the burst, you start getting these massive stars, these very massive stars, which form your specific star formation rate increases tenfold, and you start getting all of these remarkable signatures over here. And finally, then these really, really large bursts over here, these extreme bursts of star formation are what start giving you these very massive stars, and you get these carbon-4 signatures as well as these nitrogen signatures over here. So putting this all together, this suggests that this sort of exotic physics, which we saw within the first 1 to 2 years with JWST of these remarkably bright objects, might not actually be the exception to the rule. They are part of the rule. They just represent the tail end of these distributions. So I'll finish there with my conclusions, which are that these high redshift galaxies look remarkably different to the galaxies we see at redshift 0. And we can infer all of this by analyzing over 2,000 spectra from JWST at redshifts greater than 5 now. A number of these objects show apparently exceptional properties, exotic properties, and so the natural question is, do these trace sort of extreme outliers, or are they governed by exotic physics? And we have gone some way towards answering this question through the largest spectroscopic sample of redshift greater than 10 galaxies within the first 500 million years of the universe. And if we compare the recent star formation histories of these objects, we find that these apparently anomalous properties are actually easily explained just by the burstiness of star formation in these early galaxies. And so finishing up, let's get back to Louis' prediction of, they're small, blue, and bursty. Actually, the answer is they are small, blue, and bursty, but they're also large, red, and passive. So thank you very much for your time.